All right, let's just jump right in. String theory. You've probably heard it called the theory of everything, right? It's this gorgeous, super elegant idea that everything in the universe, you, me, the stars, is all made of these tiny vibrating strings. The dream is to unite all of physics into one single beautiful equation. But, and it's a huge but, there's a major catch.
And that's really the big question we're tackling today. If string theory is all happening on a scale that's impossibly small, with energies that are ridiculously high, how in the world do we ever prove it's real? This whole thing is basically a cosmic detective story, and physicists are the ones on the case.
So here's the core problem. To actually see one of these strings, to get that direct smoking gun evidence, you would need a particle accelerator billions, and I mean billions of times more powerful than anything we can build today. The energies are just astronomical. It means our main suspect, the string itself, is impossible to bring in for questioning.
But hey, any good detective will tell you, when you can't get a direct confession, you look for indirect evidence. You look for fingerprints, for accomplices, for any clues left at the scene. And for string theory, physicists have had two really big leads they've been chasing for a long time.
Okay, lead number one is this really cool idea called supersymmetry. You'll often hear it called SUSY for short. The thinking behind it is that the universe is just fundamentally balanced. And almost every version of string theory predicts that for every particle we know, there's a hidden, much heavier superpartner particle hanging around somewhere.
So, for example, for every electron, there should be a selectron. For every photon, a photino. They call these hypothetical guys sparticles. You can think of them as the mystery accomplices in our cosmic case. If we could just find one of them, wow, that would be a massive break for string theory.
Lead number two sounds like it's straight out of science fiction, extra dimensions. See, string theory just doesn't work in the 3 dimensions of space plus 1 of time that we all know. For the math to work, it needs 10, sometimes even 11 dimensions. The idea is that these other dimensions are curled up so incredibly tiny that we just don't notice them. But they might just change the laws of physics, like gravity, at really small scales. Another potential fingerprint.
So, to go hunt for these clues, these superpartners, and any weird signs of extra dimensions, our detectives built the most powerful interrogation room on Earth, the Large Hadron Collider, the LHC over in Switzerland.
And the hopes for the LHC were just sky high. The idea was to smash protons together so hard that you might shake loose some of these new, heavy sparticles. Physicists even thought they might create tiny, fleeting microscopic black holes, which would be a dead giveaway that gravity was leaking into those extra dimensions. They were looking for a whole new layer of reality.
And then, the results started rolling in. And it was a huge plot twist. The LHC worked perfectly. It found the Higgs boson, which was the final missing piece of our current theory of physics, a massive, Nobel Prize-winning achievement. But the smoking guns for string theory, the sparticles, the mini black holes, nothing. They were nowhere to be found. The lab just went quiet.
And this wasn't just a vague feeling. The data was specific. Take this, for example. Physicists watched how often a certain particle, a B meson, decays. Most of the supersymmetry models predicted this decay would happen way more often than we thought. But what did the LHC find? It happens about 3 times in a billion, which is exactly what the old theory predicted. Another lead gone completely cold.
So with the investigation on Earth hitting one dead end after another, our cosmic detectives did what any good investigator would do. They expanded the search. They turned their attention from the sterile lab to the ultimate crime scene, the entire universe, which is basically the biggest high-energy experiment you could ever ask for. So now the hunt is on for clues that are way more subtle, hidden out there in the cosmos. They're looking for ripples in space-time left over from the Big Bang. They're studying these incredibly energetic particles from deep space called cosmic rays, and they're trying to solve 2 of the biggest mysteries out there. What is dark matter, and could these giant cosmic superstrings actually exist?
Just look at this. Events like gamma-ray bursts are just mind-bogglingly powerful. By studying the light that travels all the way across the universe from these explosions, scientists can actually test if the basic laws of physics, like Einstein's theory of relativity, hold up in these extreme environments. And since string theory is built on top of relativity, any little crack in that foundation would be a huge clue.
And here's a really cool thought. We know the universe is filled with this invisible stuff we call dark matter. It's most of the matter out there, and we have no idea what it is. But what if dark matter is just the leftover wreckage from the Big Bang? What if it's made of the lightest, most stable superpartners? If that's true, solving the mystery of dark matter could finally reveal our first sparticle. Two birds, one stone.
Now this might be my favorite idea of all. Some versions of string theory predict that unimaginably long strings, stretched out by the expansion of the universe, could still be crisscrossing the cosmos today. You'd never see them, but you could use the entire sky as a detector. By watching for their massive gravity warping the super-regular signals from distant pulsing stars, the sky itself becomes this giant web for catching a superstring. So clever.
So, after all this searching, in the biggest labs on Earth and across the entire cosmos, what's the verdict on string theory? Well, for now, the case is still wide open. We've got a lot of interesting ideas, but no conviction.
And that kind of gets to the heart of it all. See, string theory isn't really one single theory with one simple prediction. It's more like a huge mathematical framework, a whole landscape of possibilities. So if one experiment comes up empty, theorists can often just tweak the model a little bit to create a new version that still works. It's what makes the theory so powerful, but also what makes it so frustratingly hard to pin down.
So let's just quickly summarize our case file. We have no smoking gun. Not direct, not indirect. Our best shot on Earth, the LHC, keeps finding results that stubbornly support our old theory. String theory itself remains this beautiful, mathematically perfect idea that just seems to have no connection to experimental reality yet. And so, the search has now gone fully cosmic.
Which really leaves us with this final, massive question. Is the evidence for a theory of everything really out there and we just need better tools or more time to find it? Or has this entire investigation, which has been going on for half a century, been on the wrong track? Maybe what we really need is a whole new kind of detective with a totally new theory to finally crack the case.